All right, so this is the Laplace transform pairs table from the textbook. I think it's super helpful. This is definitely something you're going to refer to a lot when solving these types of problems. Let's just take a look at a couple of the ones that we've already seen. For one, u of t, the unit step function, we can see that that has a Laplace. So first of all, what we're looking at here is we're looking at functions of t on the left and their Laplace transforms on the right. Okay, so this table goes both ways. If you have a function of s, you can get the function of t. Basically, you can take the inverse Laplace transform by looking at the corresponding function of t. If you have a function of t, you can get the Laplace transform of that by looking at the corresponding function of s. And of course, we already proved this one, that u of t's Laplace transform is 1 over s. We also already proved that if you remember correctly, we already proved that, let's see, what was the other one? Oh, the cosine. It was the cosine of omega t times u of t. We proved that the cosine of omega t u of t was equal to s over s squared plus omega squared. If you want to do some practice, you can always throw one of these equations into the Laplace transform, right? Remember the Laplace transform? Well, the full Laplace transform is negative infinity to infinity, so that's why I was talking about all these u of t's, right? Every single one of these functions is multiplied by u of t, because once you throw that, whatever that f of t is, times u of t in here, times e to the minus st dt, that basically converts this into a one-sided Laplace, right? Once I know that my thing is multiplied by u of t, my function, then this becomes 0, and then I'm right back where we started, which is right here. And so if you want to practice, you can definitely solve some of these expressions. We can kind of see some of the properties come to life. If you remember correctly, we talked about time shifting. So if we go look back at time shifting, it said if I shift by a factor of t in the time domain, I end up multiplying by a factor of e to the minus st in the s domain. So here, u of t is 1 over s, but u of t minus t is 1 over s multiplied by e to the minus t times s, right? So that we can see the time shift property come into play here. Alternatively, we talked about how if we take, this is frequency shifting in action right here. We talked about how if we have something like 1 over s, we know that that's the inverse Laplace transform there would be u of t. But if we shift by a in the s domain, we end up multiplying, right, u of t times e to the minus at in the t domain, or in the time domain. Okay, so you can see the Laplace transform properties at work right here in the Laplace transform table. Okay, so maybe give some of these a practice. Of course, I'm going to probably assign some of these as work for you to try and derive. Maybe the sine would be a good one to try and practice with, because we did the cosine, which was very similar, so you should be able to derive this sine. And yeah, if you have any questions, obviously, please feel free to let me know, but we're going to be referring to this table an awful lot whenever we need to take a Laplace transform or take an inverse Laplace transform. This is the table that we're going to be using. Okay? So I'll end this video right here, and in the next section, we're going to start talking about applying all of this to circuit analysis. All right, so I'll end this video here, and we'll see you guys in the next video.